Okay, so we've investigated what the idea of a limit is, and now we're going to bring that together into calculus and work out how those two things go together. First things first, when we're working out the gradient function, which is the whole point of differential calculus, we give it a special name. And the special name that we give our gradient function is f dash of x. Okay, so f of x is the function, whatever the function might be. F dash of x is the gradient function, or sometimes, or otherwise known as the derivative. Okay, and what we're doing now is working out how to actually calculate that using a method called first principles. And first principles really just means using really simple, straightforward concepts, not any particular technical rules. And the first principles that we're actually basing this on is simply the slope between 2 points. So what are the 2 points that we're talking about in our little in our example here? So here we have where are we? Here we've got our value of A and B. A is just some unknown value. We might know what it is. Generally speaking, we don't though. And we know that if this function is f of x, then the y coordinate that goes with A is simply f of A. That's enough. What we're doing here is we're adding h to A. So B is actually A plus h, some distance between these 2 points. And you might remember from our earlier lessons that the closer those 2 points are together, the better the chord will be as an approximation to the curve. So we've got this second point B, which we're going to call A plus h. So whatever this x value is, plus whatever this distance is, that's going to be our B coordinate. But because we like working in a single variable, we're going to call it A plus h. And we know that if x is A plus h, then y is simply going to be f of whatever A plus h is. So these become our 2 points that we're finding the slope of the chord that joins them, because here's the chord that's been drawn in. Using our basic rule, we've got our slope is y2 minus y1 on, now x2 minus x1. That's going to be, this is x1, this is x2. x2 minus x1 is going to be A plus h minus A, which is simply h. And so what we have here is h in the denominator. Now, like I said before, the closer these 2 points get to each other, the better the chord will be as an approximation of the slope at that point A. We've already established that you can't just use the 2 points A, because then you have a function that's undefined, because rise will be 0 and run will be 0, which is a problem. And that's where the concept of the limit comes in. We can't let the difference between these 2 points equal 0, so instead we consider what happens as we approach 0. So that distance gets smaller and smaller and smaller and smaller and smaller, but not actually 0, and we can work out what's happening by using limits. So let's go through an example. Use first principles formula to find the gradient of the tangent to f of x equals, now that says x on 4, it should say x squared on 4, so please add that in. X squared on 4 at x equals 3. All right, so looking at our first principles formula, we've got 3 variables or 3 values in there, f of A plus h, f of A and h. All right, so just over to the right, we've got f of x already, and we're just going to treat that as f of A. So then we work out what f of x plus h is, and that's going to be x plus h all squared on 4, so just subbing in x plus h. Just going to leave it like that for the moment, and we'll work out what to do with it in a minute. Now, f dash of x, so the derivative for any value of x, is the limit as h approaches 0 of f of x plus h minus f of x on h. We haven't done anything with the limit, so we write the statement down, limit as h approaches 0. Now, f of x plus h is x plus h all squared on 4 minus f of x, which is x squared on 4, all divided by h. Now, if you have fractions in your numerator, it's much easier, rather than having fractions in your numerator and then dividing by h, put your numerator in a set of brackets and multiply by 1 on h. It's much easier to work with. We still haven't done anything with the limit statement, so we write that down, 1 on h. Now, the left-hand term is going to be x squared plus 2hx plus h squared on 4 minus x squared on 4, so we can extend our denominator because they're both divided by 4. Then we cancel x squared minus x squared, and we're left with these two terms here, plus 2hx plus h squared. They've got a common factor of h. So what we're going to do is, haven't done anything with our limit statement yet, so we just write it down. I'm going to factorize that numerator. So it's h outside of 2x plus h on 4. Hopefully you can see now that we can cancel this factor of h here and this factor of h here. And what we're left with is the limit as h approaches 0. We still haven't done anything with our limit statement, so we just write it down. We've cancelled our factor of 1 on h at the front, so we're just left with 2x plus h on 4. There's nothing else that we can do to simplify that. We could split the denominator, and you can if you want, but there's no need to. Because we've simplified it as much as we possibly can, especially with respect to h, our next little step is to apply the limit statement. So f dash of x equals, we apply the limit statement, which means we sub in the value of h into the equation. Notice that we don't have a value of x for the time being, so we're just subbing in for h, and it becomes 2x on 4, which is x on 2. So f dash of x, the derivative of x, for any value of x is x on 2. We've been specifically asked for the slope of the tangent at x equals 3. So we can sub in x equals 3. When x equals 3, f dash of 3 equals 3 on 2. So f dash of 3 means the value of the slope of the tangent at x equals 3, and not the eyeballed tangent, the one that you've just done your best to estimate. It's the actual tangent. And so the slope at that point is 3 on 2. The advantage of doing it this way, rather than subbing in values of x straight away, is that you can find the gradient function for any x, and then you can just substitute it in. So for example, the slope at x equals 5 is going to be f dash of 5, which is 5 on 2. And so we can calculate the slope at any point using first principles. That's it.